This is the presentation for chapter number 4. We are currently around page 57 in the slot notes. We're going to be taking a look at some chemical reactions, defining them, and how to balance them. And then we're going to take a look at some of the math of chemical reactions called stoichiometry. Chemical reactions basically is a process where starting material or reactants, their composition is changed to products. Some of the signs for chemical reactions are color change, gas evolving or bubbling, precipitation, heat change, and pH change. And we'll take a look at some of these in this chapter in more detail than others. So what we first need to do is a process in which one or more substances change into one or more new substance, like we said, is a chemical reaction. So we need to determine whether each of the following changes is a chemical reaction, and then we need to provide some support. Okay, so burning leaves is a chemical change because we end up with a change in energy, color, smell. We end up with a phase change. Definitely can smell those burning leaves in the fall, and we get a solid that eventually turns into a gas. And we definitely get the leaves going from brown to black. Mowing the lawn is just a physical change because all we're doing is changing the particle size. And baking a cake is a chemical change, and how you know that, again, you get changes in energy because you got to add energy to it instead of removing energy, like with or you have to add energy instead of energy being released, like with the burning of leaves. Definitely get a color change, especially if you cook it too long, then it'll go from brown to black. You definitely can smell the cake baking in the oven, and you start out with the liquids in the batter, and eventually you end up with a solid. So what property do all chemical reactions have in common? Again, they produce brand new substances. So in section 4.1, we're going to basically come up with some chemical equations and basically start to learn how to balance them. So with our chemical equations, a chemical equation uses chemical symbols to represent what happens during a chemical reaction. So we can write this in words, or we can use our formulas that we started to put together in chapter number 2, writing the formulas for compounds and molecules. Or we can symbolize this by using space-filling models. We're going to stick with the writing of formulas, and so we need to understand how to read a chemical reaction. And one of the ways to read this reaction is we got 2 atoms of magnesium plus 1 molecule of oxygen gives 2 formula units of magnesium oxide, because magnesium oxide is an ionic compound, so it's going to have formula units, not molecules. We can also, from the previous chapter, talk about moles. We can go from 2 moles to 1 mole to give us 2 moles of magnesium oxide. We can also use the molar masses of these, convert the moles to grams. What we cannot do, and what this does not represent, if you look at the bottom of the screen, is it does not represent 2 grams reacting with 1 gram to make 2 grams. That these are mole ratios. So what does it mean to say an equation is balanced? And why is it important for an equation to be balanced? It's balanced when it has the same number of each type of element on both the reactants and the product sides. Okay. Equations must be balanced to accurately reflect the law of conservation of mass, which says that matter is neither created nor destroyed. Number 2, it says consider molecular, complete ionic, and net ionic equations, which we'll eventually get to. So this will give you some idea of what we're going to be covering in this chapter. And it says molecular equations are written without regard to dissociation or breaking apart of any ionic reactants or products, because ionic compounds, when dropped in water, will break apart into their individual ions. The formula is represented as, again, neutral substances. Complete ionic equations more realistically represent the dissolved ions, so we'll separate them out. And in a net ionic equation, they represent the dissolved ions that are chemically or physically changed, or those that are acting. And what we'll eventually do is we'll omit spectator ions. Okay, and in what circumstances would the complete net ionic equation for reaction be identical? If there are no spectator ions. And we'll go into that in a little bit more detail in a couple slides down the road. Before we can take a look at net ionic and ionic, we need to figure out how to balance a chemical reaction. So in order to balance a chemical reaction, we write the correct formulas for the reaction on the left side and the correct formulas for the products on the right-hand side. We learned how to write formulas in Chapter 2. So we've got ethane reacts with oxygen to form carbon dioxide and water. So ethane is C2H6. And then we're going to add oxygen. Remember, it's diatomic. Remember Brinkelhoff. And that's going to give us carbon dioxide and water. So what we're going to do is we're going to change the numbers in front of the formulas, or add coefficients, to make the numbers of atoms of each element the same on both sides of the equation. Okay? We never change the subscripts, or we change the compound. So if you notice, we put a subscript in front, we don't change the subscripts. So we start by balancing those elements that appear in only one reactant and one product. So in this case, what I'm going to do is I'm going to start with carbon or hydrogen, but not oxygen. I'm going to pick the carbon because it's the first one that shows up, and we read from left to right. So I've got 2 carbon atoms on the left, but I only have 1 carbon atom on the right. So I need to get this to balance according to law of conservation of mass, and I balance it by adding coefficients. So what I'm going to do is I'm going to multiply the CO2 by 2, and so I'm going to put a 2 in front of the CO2. I'm now going to take a look at the hydrogen. Notice I'm taking a look at one element at a time. And I've got 6 hydrogens on the left, and I've got 2 on the right. And so what I'm going to do is I'm going to multiply the H2O by 3, and I'm going to put a 3 in front of the H2O. Now what I'm going to do is I'm going to balance those elements that appear in 2 or more reactants or products. Well, I put coefficients on the right-hand side, so I'm going to start on the right-hand side. And so I've got 2 oxygen on the left. I've got 4 oxygens on the right, multiplying by the 2 that's in front, the coefficient times the subscript. And I'm going to multiply the oxygens in water by 3, because there's a 3 and there's only 1 oxygen in it. And I end up with a total of 7 oxygens on the right. And if you notice, we started with 2 oxygens on the left. Well, if I multiply the oxygens by 7 halves, which would mean multiply the whole equation by, or multiply the oxygens by 7 halves, we put a 7 halves in front of O2. The issue we run into is we typically deal with whole number coefficients. Could we leave this as a fraction? Yes, but it's not appropriate. So what we're going to do is we're going to multiply both sides of the whole equation by 2 to remove that fraction. And so we end up with a 2C2H6 plus 7O2 gives 4CO2 and 6H2O. This is about the hardest equation you're going to balance in Chem 111. Yeah, they get a little bit trickier in Chem 112, but we have a set of rules similar to those oxidation rules that we saw in chapter number 2, and we'll follow those rules for balancing redox equations or oxidation reduction reactions. So we want to ultimately check to make sure that you have the same number of each type of atom. And if they're equal to each other, then ultimately our equation is balanced. So some hints for balancing chemical equations is determine to write the correct formulas for the reactants and products. Especially remember the diatomic. Okay, you can only change the coefficients, and they're integers, whole number coefficients, not the subscripts. Some of the tricks that we're going to take a look at is start with polyatomic ions, then atoms that appear in the fewest places, because then we can kind of balance a couple of them at the same time, and you'll see what I mean when I'll show you a couple examples. H2O is really HOH. It's not two hydrogens and an oxygen. That has to do with acid-base chemistry. So just kind of chalk that in your head. I'm going to show you how to use that. And then later on in this chapter and then the semester, what you're going to find is how true that is. Okay, we're going to do oxygen last, because usually it shows up in more than one place. And finally, ask yourself, do you have the same number and kinds of atoms on both sides of the reaction arrow? So let's take a look at a couple examples. And the first one's kind of a trick question, because if you go to take a look, the equation's balanced as written. And too many times as students, you want to add coefficients and keep adding coefficients and keep adding coefficients, when in reality this should be relatively simple. You should only be adding one or two coefficients. And like I said, as students, you have a tendency to keep adding things to the equation. Our balanced equation should be the simplest ratio of the coefficients. So theoretically, you could put a 2 in front of each of these. You would have the same amount on each side, but we want the simplest ratio. So this equation is already balanced. So let's take a look at this equation. We got H2O. And if you remember with the H2O, I said treat it as HOH. And how you know to treat water as HOH is if you'll notice there's an OH on the right-hand side. So if I take HOH and I go to balance this, I'm going to take a look at the equation and I'm going to look at the hydrogens, because sodiums look like they're already balanced. I'm going to take a look at hydrogens, not OHs. So what we need to do is when we go to balance the hydrogens on both sides, what we're going to find is I have two hydrogens on the right and I have one hydrogen on the left. Notice the red H in front of the HOH. So that 2 in front of the H2O right now is just multiplying the hydrogen. Well, if I multiply the hydrogen by 2, remember the other thing is keep polyatomic ions. Hydroxide's a polyatomic ion, so I have two OHs on the left-hand side, which means I can put a 2 in front of the OH on the right-hand side. So now my OHs will balance each other. And now listen to what I'm going to say next. If you notice there's a 2 in front of the Na, what do you think should be in front of the Na on the left-hand side? And if you said 2, you were absolutely right. Because sometimes we don't go through and just add up. If I've got a 2 in front of the Na on the right, I probably need a 2 in front of the Na on the left. So let's take a classic equation from biology, hydrogen peroxide breaking into water and oxygen, and this one used to drive me nuts until I read somewhere about this odd-even rule, and it's starting to show up in chemistry textbooks. And what the odd-even rule says is that if you have an odd number of atoms on one side and an even number on the other, at minimum you're going to need to multiply the odd one by 2. And what I've found in my years of experience is that 2 is usually the coefficient you need in front of the odd one. So if we take a look at our equation here, you'll notice I've got two oxygens on the left, and I've got 3 oxygens on the right. So I've got an even number of oxygens on the left and an odd number on the right. So if I put a 2 in front of the H2O, so now I have an even number of oxygens on the right, 2 from the H2O and 2 from the O2. And if you'll notice, I put a 2 in front of H2, or you could go 2 times 2 is 4 hydrogens, but I would look at this and go, oh, I got 2 H2. I probably need a 2 in front of the H2 on the left-hand side, and lo and behold, my equation is now balanced. So let's take a look at the odd-even rule again. I'm going to put a 2 in front of the KClO3 because I've got 3 oxygens on the left and 2 on the right. I didn't worry about the KCl because I have a KCl on both sides. So I'm going to put a 3 in front of the O2 because 2 times 3 is 6. So I need 6 oxygens on the right. I have a 2 in front of the KCl on the left, so I'm going to put a 2 in front of the KCl on the right. And again, this is an example of the odd-even rule that we talked about on the previous slide. Okay, so let's take a look at an equation that's got some polyatomic ions. How do I recognize? See, there's things in parentheses. You got an SO4 in parentheses, and you got an OH in parentheses. They're all listed on that chart on the back of your periodic table. And so when I go to take a look at this, the first thing that kind of pops out to me is I've got these things in parentheses that look like each other. And so we've got the unique polyatomic ion, and we also have an odd even. So we can kind of do two things at the same time. And when we do that, it's going to make this equation, I think, really easy to balance. Because if you'll notice, I've got an odd number of OHs on the right-hand side. So I'm going to put a 2 in front of the aluminum. And because I put a 2 in front of the aluminum, I've got 6 hydroxides. I need 6 on the left, so that's why I put a 3 in front of the calcium. If you'll notice, I've got a 2 in front of the aluminum, but I've got 2 Als on the left, which means if I got a 3 in front of the Ca on the left, I'm going to need a 3 in front of the Ca on the right. And if I was to go through and add up all the atoms, what I find is that this equation is balanced. So let's take a look. I've got aluminum plus hydrochloric acid gives aluminum chloride and hydrogen. And so I'm going to start out by putting a 3 in front of the HCl, because I had 3 chlorines on the right in the AlCl3. And the issue I'm going to run into is I've got an odd-even issue going on, because now if you notice, I got an odd number of hydrogens on the left and an even number on the right. So what I'm going to do is I'm going to change that odd coefficient into an even coefficient by multiplying it by 2. And when I put a 6 in front of the HCl, that means I'm going to have to put a 3 in front of the H2 to have 6 hydrogens. I'm going to need to put a 2 in front of the AlCl3, so I have 6 chlorines. I've put it now, have a 2 in front of the Al, so I need a 2 in front of the Al on the left-hand side. And then my equation is balanced. So here, let's go back to one of those combustion ones where we started. So the first thing I'm going to do is I'm going to look for the single element. I'm not going to worry about oxygen. It shows in 3 different places. So I'm going to put a 2 in front of the CO2 because I'm trying to balance the carbons. I'm then going to take a look at the hydrogens. And when I add up all the oxygens, 2 times 2 from the CO2 plus 2 from the water, I get 6 oxygens. This is convenient because I got an even number of oxygens on the right. I've got an even number of oxygens on the left, so 6 divided by 2 from the O2. I need the coefficient of 3 in front of the equation, and the equation's now balanced. On this one, I'm going to take a look at for a unique atom. So I'm going to start out with fluorine. And because I've got 4 fluorines on the left, I need 4 fluorines on the right. And now when I add up my hydrogens, I have 2 hydrogens on the left plus 4 is 6. And so I'm going to need a 3 in front of the H2O. And my equation is balanced. Again, this is one of those type that if you keep going around, you have a tendency to go around and around and around, and you end up with like a a 4 in front of the SF4, and you end up with a 12 in front of the H2O. Start with the unique atom and then work from that point. So I got to balance the equation. I've got PCl5 plus H2O, and I've got POCl3 and HCl. And I could either look at the unique chlorine atoms and try and make 5. The other clue that I have is I have an H2 on the left and I have an HCl on the right. So I'm going to go ahead and put a 2 in front of the HCl for both of those reasons. And the interesting thing is once you put that coefficient in, this equation is now balanced. I've got H2 plus I2. This kind of looks like an odd even rule. H2 and I2. So I just need a 2 in front of the HI in order to balance this equation. So I've got P4Cl2, PCl3. I'm going to put a 4 in front of the PCl3 because I got 4 P's on the left. And notice I'm going to multiply that 3 in the chlorine by an even number. 4 times 3 is 12. 12 divided by 2 is 6. So I'm going to put a 6 in front of the Cl2. And my equation is now balanced. Okay, again, I started with the unique phosphorus atoms. If I had started out with the chlorine, I probably would have put a 2 in front of the Cl3 to make it even, and then realized I'd have to double the amount for the phosphoruses for them to balance out. So number 5 from the end of the chapter says write a balanced molecular equation, which means just write what we've been doing, describing each of the following chemical reactions. So I want solid calcium carbonate is heated and decomposes to a solid calcium oxide and carbon dioxide. So I got calcium carbonate. The carbonate comes in that chart of polyatomic ions. Calcium's +2, carbonate's -2. And it's going to break down into calcium oxide, Ca +2, oxygen -2, so it stays CaO. I've used that example a couple times in chapter number 2, plus carbon dioxide. Well, what we need to do is we need to balance the equation. The tricky thing with this equation is it's balanced as written, and that's going to happen more often. It's not all the time, but it comes up fairly often, or you're just going to have to put 1 or 2 coefficients in. Okay, so let's take a look at number 5. We've got butane, which is like what you find in a lighter. And it's going to react with oxygen. It's diatomic. Remember Brinkelhoff, that's one of the 7 that are diatomic. And I'm going to get complete combustion, so I'm going to get CO2 and H2O. Well, to balance the equation, I'm going to start with carbon, because I'd either start with carbon or hydrogen. So I'm going to put a 4 in front of the CO2. I'm going to put a 5 in front of the H2O. And 4 times 2 is 8, plus 5 is 13. So I'm going to get 13 halves of oxygen, because it's an odd number. So if you remember in our very first example, when we had a fraction, we multiplied the whole thing by 2 to get rid of that 2 in the denominator. And we end up with 2C4H10 plus 13O2 gives 8CO2 plus 10H2O. Okay, so in this problem, we've got water vapor reacts with sodium metal, and it's going to produce sodium hydroxide and hydrogen gas. Be careful, hydrogen's diatomic. This has got water in it, and you see the OH on the right-hand side, so we're going to split water into HOH. I've got 2 hydrogens on the right, so I'm going to put a 2 in front of the H2O, because that 2 is going in front of the H and in front of the OH. So I'm going to put a 2 in front of the NaOH so that I've got 2 OHs on both sides. I have a 2 in front of the Na. So put a 2 in front of the Na, and now my equation is balanced. So on this one, we've got colorful fireworks, and we want to write the formulas for barium nitrate and potassium chlorate. So we go get the polyatomic ions from the chart on the back of the periodic table. And barium nitrate, barium's +2 and nitrate's -1. Potassium is +1 and the ClO3 or chlorate's -1. So we're going to break down the potassium chlorate. And it's going to produce potassium chloride and oxygen. This is an odd even. Notice 3 oxygens on the right. Sorry, 2 oxygens on the right, 3 on the left. So we're going to put a 2 in front of the KClO3. We need to make sure we balance our oxygens, and then I have a 2 in front of the KCl, so I'll put a 2 in front of the KCl. Okay, so now we're going to break down the barium nitrate. And this is going to become an odd even. If you notice, there's an even number of oxygens. 2 times 3 is 6 on the left-hand side. But on the right-hand side, I've got 2 from the O2 and 1 from the barium oxide. So I'm going to put a 2 in front of the barium oxide, which means I'm going to put a 2 in front of the barium nitrate. And so if I take a look, I've got 4 nitrogens. That's 2 from outside the parentheses and 2 from 2 in front of the barium. And when I go to do the oxygens, I've got 2 times 3 is 6 from just outside the parentheses, then multiply by the 2 in front of the barium. So I've got 12 oxygens, but I got to subtract the 2 from the barium oxide, which is going to give me 10. 10 divided by 2 is 5, and so I end up with 5 O2. The other type of equation we can balance is structural equations. And what I do with these is I just cross off things that look similar. So if you notice, I'm going to cross off all the hydrogens. And then I'm going to cross off the carbons. Cross off the oxygens. And if you'll notice, what I have left is sodium for the sodium hydroxide, a hydrogen, and an OH. And remember, we said water breaks apart into HOH. If you have an HOH, it's going to produce water, and that's where I get the H2O from. We can classify our reactions, and you may have seen this before because this is classic in a high school level chemistry class, is to break basically reactions into 4 or 5 classifications. Sometimes combustion's not on this list in some textbooks. So this is a synthesis reaction. It's a reaction where 2 reactants combine to form 1 product. And so we got sodium reacting with chlorine to produce 2NaCl. Please be careful. Cross off the 2 on your slot notes. The reason I put that is if you don't remember to put the Cl2 as diatomic, sometimes you end up trying to balance it incorrectly. So a decomposition reaction is just the reverse of a synthesis reaction. It's when something breaks apart. A combustion reaction is anything reacted with oxygen. Typically it'll produce carbon dioxide and water, but it doesn't have to. And those are our most complex for balancing. A single replacement reaction is a reaction where an element in a compound replaces another element in another compound. In our examples here, you'll notice that the copper's kicking off the silver and the magnesium's kicking off hydrogen. A double replacement is basically when 2 compounds kind of flip over and switch with each other. Notice the Ag and the Na are switching places in the top equation, and the hydrogen and the sodium are trading places in the bottom equation. That bottom equation is also known as an acid-base neutralization reaction. And so now we're to section 4.2. And so we're going to take a look at the new way of classifying chemical reactions. And then we're going to figure out that whole molecular, total ionic, net ionic, and then classify them and take a look at some common acid and base reaction. And then we're going to predict the solubility of some common inorganic compounds. That third page that's in your reference sheets, that solubility table, is going to help us out. So in the first section, we reviewed over the old classification system, or the one that's used in high school. And the reason that it's used is it's easy for beginning chemistry students to understand. The problem is it leaves a lot of things out and ideas out. So chemists actually use a more detailed system, and the four most common types of reactions that are found in aqueous solutions, or the ones that we find at a little bit higher level chemistry, is precipitation, acid-base, oxidation reduction or redox, or gas evolving reactions. And we'll take a look at each of these. So water covers about 70% of the Earth's surface. So many reactions occur in water. Most of the reactions in your body occur in body fluid. So water's a polar molecule and has a dipole. Okay, dissolves polar and ionic compounds. Okay, ionic compounds dissolve pretty readily. Sodium chloride or salt dissolves pretty easily in water. And so let's take a look at solutions. We talked a little bit about this when we took a look at molarity, but it's good for us to stop and take a look at this again to have some idea of what's going on in our reactions that occur in water. Okay, so solution's a homogeneous mixture of two or more substances. The solute's the piece that's found in the smaller amount, and the solvent's the one that's found in the greater amount. You can have more solutes than just one. It can be several of them. Look at the soft drink. Its solute is sugar and carbon dioxide. Air is a mixture of a number of gases, not only oxygen, argon, and methane, but carbon dioxide and a couple others. So strong electrolytes break apart completely in solution. Weak, they have a tendency to break part of the way. And then non-electrolytes don't break apart at all. And where this leads us is to precipitation reactions. They look a lot like our double replacement reactions or double displacement reactions that we were classifying at the end of the first section. And so I've got AgNO3 plus magnesium chloride gives magnesium nitrate and silver chloride. So if we identify the major ionic species present in an aqueous solution of sodium carbonate, what we're going to find is this is going to break apart, or we're going to do the reverse of what we were doing in chapter number 2. Instead of crisscrossing, we're going to kind of reverse crisscross. And so we're going to end up with sodium carbonate going to break into sodium and carbonate ions. The major species that are found in K2SO4 is potassium ions and sulfate ions. If you'll notice, there's a 2 in front of the K plus because in order to balance these equations, the number of atoms or ions need to be the same on both sides. The trick question is glucose, and it's not ionic. One, it doesn't begin with a metal. It begins with a nonmetal. The other thing is typically you'll be given the name of the molecule if it's molecular and it doesn't break apart. So again, no ions are present, so it's molecular or molecular and covalent, or it has covalent bonds. To get back to where we started with this, we were looking at precipitation reactions. occurs when water solutions of two different ionic compounds are mixed and an insoluble solid separates out of solution. Okay. The precipitate is itself ionic because it comes from the cation and anion, one from one solution, one from the other, and they form an insoluble product in water. In order to predict this, what we do is we use solubility rules. Okay, figure out what's soluble and not soluble, and what we're going to find is the solubility rules are fairly cumbersome. Have to memorize them or look at the chart and figure things out. So chemists have gotten smart and they've created solubility tables. So we're going to use the solubility, well, technically we're going to use the solubility table because I don't like using the rules because you got to follow through them over and over again. So we're going to find out if either of the two products are precipitates. So in the first one, we're going to check on BaSO4 and KOH. Well, if I look at the BaSO4, barium sulfate, barium is 3 down on the left and sulfate's 3 back from the right. Below the SO4, you'll notice there's an I, which means the BaSO4 is insoluble. If you find the potassium, which is 4 up from the bottom, and you find the OH, what you're going to find, which is about in the middle of the chart, there's an S, which means it's soluble in water, so it's the barium sulfate. If I do the next thing for the next one and I look up iron, the problem is I got a choice of iron 2 or iron 3, and this is iron 2. So we end up with iron 2 phosphate as our precipitate. And the interesting thing is if we take a look at our next one, if we look up mercury, or if we look up potassium chloride, it's soluble. And if we look up mercury nitrate, it's got an S, which means it's soluble, which means that's not a net ionic equation or a precipitation reaction, so we wouldn't worry about it. So let's take a look at a little bit more detail. It says, consider the following pairs of solutions, copper sulfate and sodium nitrate. So all my ions present are copper, sulfate, sodium, and nitrate. And the copper and the sodium are going to trade places with each other. So I got a choice of copper nitrate or sodium sulfate. According to the table, just like our last one from the previous slide, both of these are soluble, so no precipitate forms, so there's no reaction. So now we're going to take sodium carbonate, Na2CO3, and calcium chloride, and we split out their ions. Our possible precipitates is NaCl and CaCO3. Well, calcium carbonate, chalk, is also what makes up coral reefs, okay, is not. So when we mix these two solutions together, we end up with a precipitate. And that precipitate is calcium carbonate. Net ionic equations are chemical equations that tell what reactant what was produced. Complete ionic equations gives every single species in its form in the solution. And so the net ionic equations show only what reactants or changes in the chemical equation. So to do this, we write the balanced molecular equation. We can write the ionic equation showing the strong electrolytes completely dissociated cations and anions. We can cancel out the spectator ions, or the ones that aren't doing anything, and check that charges and number of atoms are balanced in the net ionic equation. So we're going to take silver nitrate with sodium chloride. So we're going to take silver nitrate and sodium chloride. The sodium and the silver are going to trade places. And if you look on your solubility table, you would find that AgCl is a solid. So that's our balanced molecular equation. Well, if we want to write this as a as a complete ionic equation, we're going to break everything out into their ions. Notice I leave the AgCl together because it's now no longer broken apart. I'm then going to cancel out the ions that are found on both sides, so I'm canceling out the spectator ions. And if you'll notice, what I've got left is the Ag, the Cl that produces AgCl, and that is my net ionic equation. So consider the precipitation of the calcium carbonate from the calcium chloride. We had calcium, chlorine, sodium, and carbonate, and we found the product was calcium carbonate was our precipitate, and sodium and chlorine. So our spectator ions are our sodium and our chlorine. So technically what we're going to do is we're going to write a balanced equation to show the production of our calcium carbonate. So it says give the net ion equation for the following. And so find if each are aqueous or in solution. So now we're going to take a look at what those little parentheses. AQ means it's dissolved in water. S means it's a solid. L means it's a liquid. And G means it's a gas. If it's AQ, then what we're going to do is we're going to cancel it out. So barium hydroxide and potassium sulfate are aqueous because they're our reactants. And typically it's two solutions. I'm going to look on my solubility table. Barium sulfate is a solid, and if I look for potassium hydroxide, I'm going to find that it's aqueous. So to find the net ionic equation, we're going to write the equation without the spectator ions. So what I'm going to do is I'm going to pull the BaSO4 down because it's the solid, and then I'm going to write down the ions that are used to make it. So in this equation, we're going to try and find if each are aqueous. So here's our two reactants. KCl is aqueous, and we look on our solubility table, the HDNO3 is aqueous. Remember, our net ionic equations is then write the equation without the spectator ions. Well, if everything's aqueous, everything's spectator ions, and there's no reaction. So we've got this molecular equation. We want the complete ionic and we want the net ionic. Be careful that 2 needs to be changed to a 4. There was a typo. So the complete ionic is to write out all the ions but leave the solid together. And again, to write the net ionic equation, we just need to cancel out or eliminate the spectator ions. And we end up with the barium plus C2O4 gives us the BaC2O4. So this is a curious equation in that we've got a solid on both sides and we're also reacting with sulfuric acid. So if I write the complete ionic equation, I'm only going to write the ions that come from the aqueous. And so if you notice, I only have 2 ions that are being produced. And neither of them are eliminated on the right-hand side. So in this case, my complete ionic and my net ionic equation are the same. And this happens because this, like I said, it's an acid and a base, and it's just kind of a curious example. But if you'll notice, the only thing we break into ions are those that are aqueous. And if there's nothing on the opposite side, then we don't eliminate anything. So now we're going to take a look at acids and bases. Everyday life includes contact with many acids and bases. Notice that the ones on the left are mostly foods, and those are acids, and cleaning products are made up of bases. So let's take a look at some of the properties of acids and bases. Acids have a sour taste. They cause color changes in plant dyes. They turn litmus red, which is actually a fungus that's impregnated on the litmus paper. And they react with metals to produce hydrogen gas. They react with carbonates and bicarbonates to produce carbon dioxide gas, that classic baking soda and vinegar. And aqueous acid solutions conduct electricity. Bases have a bitter taste. Okay, they feel slippery. Again, they cause color changes in plant dyes. They'll turn litmus blue. And aqueous base solutions will also conduct electricity. Classic examples is NH3 ammonia. And anything that has an OH in it is considered basic. So for acids to measure them, we use what's called the pH scale. It's a logarithmic representation, and we'll go into more details on that in a later chapter. The pH is the negative log of the hydrogen ion concentration. And what we need to know now is that if it's got a pH of less than 7, it's acidic, and if it's a pH of greater than 7, it's basic. So an acid is by definition, is a species that produces hydrogen. And a base is a species that produces OH. So if we take a look at the Arrhenius acids and bases, an Arrhenius acid is a substance that produces H+. What we're going to find is H+ is a hydrogen atom that's lost an electron. So it's highly positive, so it doesn't hang out by itself. So what we find is it'll attract to other water molecules, so it becomes H3O. The Arrhenius base is a substance that produces OH in water. So a Bronsted acid is a proton donor, and a base is a proton acceptor. And the reason that we say that is if we take a look at NH3, it doesn't necessarily donate a OH, but it vicariously produces OH by pulling a hydrogen off of water, so we end up with that OH on the right-hand side. In order for something to be a Bronsted acid, it must contain at least one ionizable proton. What that means, it must be able to give off at least one hydrogen. Now, if you take a look at the bottom, you'll notice I've marked both acids and bases on both sides of this equation. So it says, identify each of the following species as a Bronsted acid, Bronsted base, or both. So HI is a Bronsted acid because it's donating its hydrogen. It's a Bronsted base because if you'll notice, it's accepting a hydrogen, and that's acetic acid. In our next example, it's giving away a hydrogen, so it's a Bronsted acid. But that exact same ion can actually accept hydrogen, so it can act as both an acid and a base at the same time. Well, strong acids ionize completely to H+. Classic strong acid is HCl, or hydrochloric acid. Produces hydrogen and chlorine. When we drop HCl into water, it completely breaks apart into hydrogen and chlorine ions. There are 6 common strong acids. Hydrochloric, hydrobromic, and hydroiodic are ones from the halogens. And then we have our oxo acids, the nitric acid, the perchloric acid, and the sulfuric acid. We don't see perchloric a whole lot because it's also a strong oxidizer. A little bit more on that story after we get done with acids and bases. Strong bases ionize completely to OH. So the easy way to recognize a strong base is that it has OH in its formula. Weak acids ionize only partially. So if we use HB, gives us the hydrogen that it donates, and technically the rest of it is a base. Remember I mentioned something about that acid-base thing on both sides of the equation? So hydrofluoric acid is a very classic weak acid. It produces hydrogen ions and fluorine ions. Less than 5% of it will break apart. Weak bases only ionize partially. Classic weak base is ammonia, NH3. And only 5%, that CH3NH3 is methylamine. Notice that NHX, that's common between both of those. Okay, whether it's an NH3, NH4, NH2, we know we're talking about amine groups. or the NHX is related to a weak base. Okay. The reason that these are bases is notice they vicariously produce OH in the equation. So if we take a strong acid and a strong base, HCl are strong acid and NaOH are strong base, what you'll notice is if we eliminate out the net ionic or the spectator ions, the only thing we end up with is we end up with H2O as a liquid. And so this is referred to as a neutralization reaction because every hydrogen neutralizes an OH. Weak acids and strong bases, the story's a little bit different. If I take a strong acid and a weak base, what you'll notice is I end up with, in the top one, NH4 and Cl. In the bottom one, if I take NH4, which is a weak acid, and react it with water, I end up with NH3 and H2O. Titrations can be used to calculate the mole of an unknown, usually acidic solution. The equivalence point is where the acid and base are equal to each other. And normally how we tell we've gotten to that is we look for a color change once we get past the end point. And we'll talk more about that in acid-base reactions, and we'll actually titrate or we'll in the lab, and we'll also take a look at plotting titration curves in Chem 112. Okay. Many metals react with acids, producing hydrogen gas, and now we're talking about gas-producing reactions. The reaction of magnesium with an acid, magnesium, our net ionic equation, gives us magnesium as a solid, and we end up with hydrogen gas. So if we break this into two half equations, notice that the magnesium loses 2 electrons, and hydrogen gains an electron. So we have our next type of reaction, which are oxidation reduction reactions. Oxidation reduction or redox reactions occur when there's a change in the oxidation state, or there's a gain or loss of electrons that causes this change in oxidation state. To review, we went over this in chapter number 2, if you remember. Rule number 1 said that all free uncombined elements have an oxidation number of 0. Rule number 2 said that oxygen has a minus or a negative 2 charge. Hydrogen is a +1. And then group 1 was +1, group 2 +2, group 17 -1. And then the sum of the oxidation numbers equals 0 unless it's in a polyatomic ion, then they equal the charge of the polyatomic ion. And if you remember, we assigned oxidation charges to individual atoms. And then we balanced them in compounds. And remember, we used this to find the Roman numerals for transition metals. So in our redox reactions, an oxidation is a loss of electrons. So the increase in oxidation number is positive. Reduction is named after what happens to the oxidation number, and that occurs because the oxidation number goes down and it gains electrons. Well, I like to use oil rig to remember this. Oxidation is loss, reduction is gain. There's also Leo goes Gur. I never could figure that one out. I like oil rig. I think it's a little bit easier to see. Oxidation is loss, reduction is gain. So let's take a closer look at oxidation and reduction. Again, it's electron transfer reactions. Remember, oil rig, oxidation is loss, reduction is gain. Okay, so the oxidation half reaction is always going to lose electrons. So if we're taking a look at reacting magnesium with oxygen, then notice the magnesium becomes magnesium 2+. We know it's 2+ because we already marked that on the periodic table during chapter number 2. And 2 times plus 2 means it's going to have to lose 4 electrons. The oxygen is going to gain electrons. And so we end up with O2, or we end up with O minus 2. If we combine these two half reactions, we get a whole reaction. We get magnesium reacting with oxygen to get magnesium oxide and a huge amount of energy, which comes off as white light. So if you take a look at an oxidizing agent, substance or reactant that is being reduced in the chemical equation, it's causing another reactant to be oxidized. A reducing agent is a substance or a reactant being oxidized in the chemical equation, causing another reactant to be reduced. Notice that this is just the opposite, that an oxidizing agent is reduced and a reducing agent is oxidized. The agent is telling you what it does to something else because it's an agent of change. It's going to cause something else to change. An oxidizing agent is going to cause something to change because it's going to cause it to be oxidized. So if we take a look, we've got zinc reacting with copper sulfate, and I've already broken these out, the half reactions for you. And if you notice, the zinc is losing reactions, oxidation is loss. And then we crisscross or flip. If it's oxidized, it's the reducing agent because it's going to cause the copper to be reduced. Notice the copper is reduced, so it's going to become the oxidizing agent. Well, we're going to take a piece of copper wire and put into silver nitrate. And what we find is the Ag is being reduced because it's gaining an electron. And so it's the oxidizing agent. So is the following reaction a redox reaction? Well, it's a redox reaction because if you'll notice, the chlorine all by itself is 0. That comes from our first rules. It's going to need to gain 2 electrons to become Cl minus, so it's reduced. The sodium starts out as 0 and it becomes a +1. We know sodium's +1 from the periodic table and from our oxidation reduction rules. And so if we know what's reduced and what's oxidized, we can then assign our oxidizing agents and reducing agents just by flipping the reduced and the oxidized. Gas evolving reactions will always produce a gas as a product. Usually it can be combustion, sometimes single replacement or decomposition reactions. They're usually redox reactions. And we've seen the KClO3 and the KCl and the O2. So we'll take a look at question number 12. It says, using the following equations, one, we need to find one that's a physical change, and that's A because it's going from ice to liquid water. Combustion reactions, it is 3 because if you notice, it's got oxygen and it also produces both CO2 and H2O. The one that's not balanced is 3, so there's our balanced equation. And the net ionic equation is number 5. Because it's only reacting ionic species are present. Number 13, what types of reactions? A is an oxidation reduction reaction. It's an addition reaction because we can add things together. B is an acid-base neutralization. Notice it's HBr, a strong acid, and OH, which is a strong base. And C is an oxidation reduction, or it's also known as a combustion reaction. Number 20A says identify the atoms that are oxidized and reduced. So we look for metals. Oxidation equals 0 in the elemental state. So nickel starts out as a +2 to go to 0. And the magnesium goes from 0 to +2. And then we crisscross, so we come up with the oxidizing agent is the nickel chloride, and the reducing agent is magnesium. In C, again, we're going to identify, we look at oxygen, it's got an oxidation number of 0 in its elemental state. And it's going to get O, so it's reduced. The carbon is going to go from a -2 to a +4. So the oxygen's the oxidizing agent, and the reducing agent is C2H4. Again, if you know the oxidizing agent's O2, the other reactant is going to be the reducing agent. How did it come up with the charges for the oxygen? Remember going around the block? In this one, I've got I2 is going to go from a 0 to a -1. It's reduced. Oxidizing agent's I2, which means the reducing agent is going to be the K2SO3. How did I know the S goes from a +2 to a +2.5? Again, I went around the block. But once you basically realize that iodine's the oxidizing agent, the other reactant needs to be the reducing agent. So I've got HCl with calcium hydroxide. So I got a strong acid, strong base. It's going to give water, an ionic compound. So I got HCl and CaOH. So I'm going to get water and calcium chloride. Remember, water's HOH. So I need a 2 in front of the HOH. So I put a 2 in front of the HCl, and now my equation is balanced. Let's see, we got diamonds are pure carbon and oxidized. So it's a combustion reaction. Carbon plus O2 gives CO2. Notice it doesn't always give water. This is section 4.3. Now that we've learned to classify reactions and balance reactions, now we need to take a look at the math that goes with them, or how to relate the masses to chemical reactions. Okay. Chemistry is quantitative, and atoms differ not only in their atomic number but in their mass. Remember, mass number was the number of protons plus neutrons. But when we take a look at those atomic weights or atomic masses on the periodic table, they're weighted averages of the isotopes. And then we use those masses to find chemical formulas and find the mole ratios in chemical formulas. And now what we're going to do is we're going to take a look at the mass relationships in chemistry, or more specifically, the mass relationships in chemical reactions. So the first thing we need to take a look at is what's called the mole ratio. This comes from those coefficients that we were using to balance equations in the previous sections. And the simplest type of problem that we have in the stoichiometry section is mole to mole problems. They're basically one step. But if you'll notice, we're going to take 2.35 moles of O2, multiplication sign division bar. That should sound familiar. But we're not going to worry about canceling out the moles because we want to go from moles to moles. So we want to get rid of the O2 because if you notice, we're looking for the moles of water. So I'm going to put 15 O2 on the bottom. Notice 15 comes from the balanced equation. And then I'm going to put 6 H2O on the top because we're looking for water. And if you'll notice, this is pretty simple. 2.35 times 6 divided by 15. Please don't worry about simplifying these fractions. And so we take 2.35 times 6 divided by 15, and we end up with 0.940 moles of H2O. Three significant figures because I started with the 2.35. So if we take a look at another example, we've got 0.36 moles of lead. Multiplication sign division bar. Let's get rid of the lead because we're not looking for lead. We're looking for how many moles of hydrochloric acid. So the hydrochloric acid is the HCl. Remember to pull the 2 down from the balanced equation. We take 0.36 times 2 and we end up with 0.72 moles of HCl. So now what we're going to do is we're going to take a look at a little bit more complex problem. We're going to take a look at mass to mass. So what we're going to do is we're going to convert grams to moles, then use that mole ratio that you just saw in the 2 previous slides, and then we're going to convert those moles back to grams. So it says determine the mass of carbon dioxide produced when 0.85 grams of butane reacts with oxygen according to the following equation. So I've got 0.85 grams of butane. That's the C4H10. I'm assuming you can figure that out because the other three should be fairly obvious considering it's oxygen, carbon dioxide, and water. Multiplication sign division bar. We're going to put grams on the bottom. We're going to put moles on the top. We're going to add up the mass of 4 carbons and 10 hydrogens. And we end up with 58.05. If we were to stop right here, this would be our grams to moles conversion. We were doing that in chapter number 3. But we're looking for the mass of carbon dioxide. So we're going to get rid of the butane first. So the butanes will cancel each other out. We're going to look for CO2. So I'm going to put an 8 in front of the CO2. At this point, if I was going to stop the problem, I would have moles of CO2 in the problem. But we're not looking for moles of CO2, we're looking for grams of CO2. We're going to take a look at the gas laws. We'd stop here and then just plug this into an equation called the ideal gas law equation. But we're looking for grams. So let's get rid of those moles. We're looking for grams, so I'm going to look directly to the left. I need the mass of the formula that's to the left. So I need the mass of just CO2, and that's 44.01. And at this point, we would just put the numbers in our calculator. Take 0.85 divided by 58.05 times 8 divided by 2, and then multiply by 44.01. And we end up with 2.6 grams of CO2 because we just started with 2 significant figures at the beginning. Okay, so let's take a look at another equation. We've got 5 chlorines plus 2 phosphoruses gives us 2 phosphorus pentachloride, or PCl5. So I've got 3.5 grams of chlorine and an excess amount of phosphorus. So I take the 3.5 grams of chlorine. We're going to get rid of the grams. Remember to multiply the mass of chlorine by 2 because there's Cl2, so we get 70.90 instead of 35.45. We're then going to get rid of the Cl2 by pulling the 5 down from the equation. We're going to leave a 2 in front of the PCl5. We're looking for grams, so we need another multiplication sign. And if you take 1 phosphorus and 5 chlorines and add them together, we end up with 208.22. And then if we put this into our calculator, we end up with 4.1 grams of PCl5. So let's take a look at a couple of problems from your book. On number 42, we're going to use the equation for making sodium chloride. And we want to know how much chlorine is required to react with 10 grams of sodium metal. So notice we don't always have to do reactants and products. So we got 10 grams of sodium metal. So we're going to get rid of the sodium, the mass of sodium, by dividing it by its molar mass. We then need to use the mole ratio from the equation. Is a 2 in front of the Na. And then we got the Cl2. And then if you remember from a previous problem, the mass of Cl2 is 70.90. We get rid of the moles. And to find the answer, we're just going to take 10 divided by 22.99 divided by 2 times 70.90. And we end up with a mass of 15.4 grams of Cl2 needed to be react with the sodium. And if we had 10 grams of sodium and 15.4 grams of chlorine, we'd say it's in stoichiometric equilibrium, which means we've got the right amount of both of them for this reaction to take place. Number 44, we've got magnesium plus hydrochloric acid. You'll use this reaction to find the molar volume of hydrogen gas at the end of the course. So we've got 5 grams of HCl. We're going to get rid of the grams of HCl by divided by the mass of 1 hydrogen and 1 chlorine. We're looking for hydrogen gas. We're going to put the hydrogen on the top and the 2 HCl's on the bottom. And if I was going to find the molar volume or find the volume of this gas, what I would do is I would then take the answer to where I am right now. I'd have moles of hydrogen and plug it into the ideal gas law equation. And we'll do that in the last chapter of this semester for Chem 111. But for right now, we're looking for the grams of hydrogen. So it's 2.02. Hydrogen times 2 is 2.02. So 5 divided by 36.46 divided by 2 times 2.02 gives 36.8 grams of hydrogen will be produced. So now we're going to expand on this idea of mass to mass, and we're going to take a look at this thing called reaction yields. Remember I talked about that stoichiometric equilibrium? Well, in an ideal world, all our reactions would be in stoichiometric equilibrium. But what we find is we don't always get all the reactants and products that we would expect. So we're going to start taking a look at this idea here in Chem 111, but we'll go into a lot more detail when we go to take a look at equilibrium as a higher level concept from Chem 112. So the first thing we need to take a look at is limiting reagent. If you take a look at our example here, what you'll notice is when we go to react our NOs and our O2s, if you look at the bottom of the screen, those three little things that are circled over are O2s that didn't get used up, so they're said to be in excess. And the NOs, if you'll notice, there's no NOs left over, little blue and white circles, so it's said to be limiting. Because the reagent that gets used up is the one that's limiting. It determines the maximum amount of product you can get from a reaction. So typically in a limiting reagent problem, the most simplest form is we just complete 2 mass-to-mass problems, just like what we're doing, and then we'll pick the one with the lowest value, because the one with the lowest value starts with the limiting reagent. So on this one it says, what mass of NaC will be produced by the reaction of both 58.7 grams of sodium iodide and 29.4 grams of chlorine. So we're going to start with the sodium iodide because it just comes first in the problem. And we're going to do like what we were just doing in the previous section. We're going to put the grams of NaI in the bottom. And we're going to put moles in the top. So if I add up 1 sodium, 1 iodine, I end up with 149.90. Once I've gotten rid of the grams, then I need to get rid of the NaI. And I'm looking for sodium chloride. So I'm going to put the sodium chloride, notice the 2 in front of it. And so at this point, I would have moles of NaCl. And there are some books that would have you stop here, compare the moles of 2 problems, and then finally do the grams. But I just prefer to just finish out the problem. So I can put moles on the bottom, put grams on the top. The molar mass of sodium chloride is 55.85, 1 sodium, 1 chlorine. And I end up with 21.9 grams of NaCl if I started with the 58.7 grams of NaI. So now what I'm going to do is I'm going to do the exact same thing, but I'm going to start with the 29.4 grams of chlorine. So if you'll notice, I've put the grams on the bottom, moles on the top. Mass of 2 chlorines is 70.90. Multiplication sign division bar. I'm going to put the chlorine on the bottom, 2 NaCl on the top. Get rid of the moles. Molar mass of NaCl is 55.85. So I'm going to do the exact same thing I did at the top. So there's no need to stop at moles and then rethink about what you're doing. Like I said, I like to just go all the way to the end of the problem. And then it's pretty simple to take a look that our smallest number is 21.9. So that means 21.9 grams of sodium chloride will be produced because NaI is the limiting reactant. So let's take a look at a more simplified version of this. We're starting out with moles of E2O5 and moles of calcium, and we want to know moles of vanadium. Well, a moles to moles problem only takes one step. So I can start with the moles of the V2O5, and I end up with 2.0. Notice I multiply by 2 because there's a 2 in front of the V. And now I'm going to start with the calcium. And so I'm going to take 4 times 2 divided by 5 is 1.6. And so what I would do is I'd pick the smaller of the two, which means I'd end up with 1.6 moles of the vanadium, and the limiting reagent would be the calcium. So let's go back and take a look at a grams to grams problem. And this is asking which is the limiting reagent. Well, let's start out with 40.0 grams of an H3. Divide by 17.04, put moles on the top. And so I'm going to put the mole ratio, 4NO over 4NH3. I could have picked 6H2O. This doesn't tell me which one to use. It's just asking for the limiting. So I just picked one or the other. And I just chose 4NO because it comes first in the equation. I could have used the 6H2O on the bottom and compared them. And so if I take this out to a grams to grams problem with the NO, I end up at 70.4. Get rid of the 32, or use the 32 to get rid of the 50, because there's 32 grams molar mass of O2 times 4 divided by 5O2, and end up with 37.5 grams of NO. Like I said, some books will stop at the end of the NO and then have you compare the moles, but I prefer to just do grams to grams problems just for the practice and to be able to just keep going, because we'll use that idea in several different places in chemistry. And so we'll pick the smaller of the two, and that's the 37.5 grams of NO, and O2 would be the limiting reagent. Reaction yield is actually what we've been calculating. Okay. Theoretical yield is the amount of product that would result if all the limiting reagent reacted. That's what we've been calculating. The actual yield is what you would actually collect if you did the reaction in the lab. So to find the percent yield, it's actual yield over theoretical yield times 100%. So the strategy for a percent yield problem is complete a mass-to-mass problem, or just complete a stoichiometric problem, and just put the stuff that you actually collected or somebody collected in the lab divided by what you calculated, because you calculate the expected, times 100%. To turn that into a percent, you get the percent yield. So it says determine the percent yield for the reaction between 27.6 grams of potassium and excess O2. So this is not a limiting reactant problem. That 23.6 grams of K2O is produced. That is the actual yield. So we need to calculate an expected yield. So in this case, it's going to be a mass-to-mass problem. So I'm going to start out with 27.6 grams of potassium. Get rid of the grams. Put moles on top. Mass of potassium is 39.10. We're looking for the percent yield. So what we're going to do is we're going to keep on going. I'm going to put 4K in the bottom. 2K2O on the top, because we want to know what the theoretical yield and then we can calculate the percent yield. So we need the grams of K2O, so we get rid of the moles. Grams on top, take the mass of 2 potassiums and 1 oxygen, end up at 94.20, and we end up at 33.3 grams of K2O. This is our expected yield. So if you remember, 33.3 grams expected, it's actual over expected. Whoever did this experiment got 23.6 grams. Multiply that by 100% to turn it into a percent. And we end up with 70.9% as our percent yield. So here's a simpler problem because it says a student isolated 25 grams, and I want it to calculate the theoretical yield was already calculated. We would expect 81. So if the 81 grams is expected, we would normally calculate that, but somebody's already been kind enough to calculate it for us. 25 grams is what they actually got. It doesn't look like they did really well. So when we multiply this times 100, we end up with 31%. And I was kind of being facetious a little bit. 25 grams out of 81 grams might be an extremely high yield for a reaction, especially if it's an organic reaction. Again, 31% for this yield. So I've got, let's see, a sample of carbon dioxide, and I've got 1.31 grams of calcium carbonate. What is the percent yield of this reaction? So I'm given an actual yield, and I'm given a amount that I started with, so I'm going to have to do a grams to grams problem. So I'm going to take 1.31 grams of calcium carbonate, get rid of the grams by dividing by the molar mass of calcium carbonate, which is 100.11. Put calcium carbonate on the bottom because I'm looking for CO2. Mass of CO2 is 44.01. And I end up with 0.576 grams of CO2. Whoever did this reaction, we're expecting them to get 0.576. They actually got 0.53. Multiply times 100%. And we end up with about 92%, which is really a fantastic yield for the most part for most reactions. Anything over 90% is really considered pretty good. And again, if we get 92%. So in the previous section, we've been using basically grams, but if you remember at the end of chapter number 3, we talked about this thing called molarity. And if we use molarity, we can do titrations and gravimetric analysis. Titrations is comparing two solutions. Gravimetric analysis is basically when you use a solution to test something else, whether it's a gas or a liquid. And then we'll take a look at how to substitute in molarity into these problems. So here's a kind of a roadmap that shows all the different types of reactions we can do. We're not going to worry too much about Avogadro's number. But if you take a look in this section, what we're going to do is we're going to take a look at using liters. So we're going to use use molarity. Eventually what we're going to do is we're going to see that thing STP, and we'll add in the idea of gases, but we won't do that until the end of the course. So if you remember, molarity is a concentration, and it's the moles of solute over liters of solution. So we can use this as a conversion factor instead of grams per mole or Avogadro's number per mole. We can use moles per liter. Okay. So the molarity can be used to calculate the number of moles of solute in a given volume of solution, or the volume of solution containing a given number of moles of solute. So now what we're going to do is we're going to apply the molarity to a balanced chemical equation. So we're going to use it as a conversion factor. So here's our grams to grams problem. Took 7.35 grams of zinc divided by the 65.39, which is the molar mass of zinc, It's a mole ratio of 1:1 between the zinc and the hydrogen. Hydrogen has a mass of 2.02 grams, and it's 0.227 grams of hydrogen would be produced if we started with a 7.35 chunk of zinc and it had an unlimited amount of hydrochloric acid. Well, in this reaction, we don't have an unlimited amount. We've got 500 milliliters, or 0.5 liters, and we've got a 1.2 molar solution. Remember, molar, that big M represents moles over liters, so now I'm using it as a conversion factor. Liters will cancel out, find moles, get rid of the HCl, find the H2, and what we're going to find is the zinc is the limiting reagent, and the hydrochloric acid is in excess. And if you were watching this reaction, it would be pretty easy. We would just watch it, and if the reaction stopped fizzing and all the zinc disappeared, then we could make a general assumption that all the zinc was used up and it was the limiting reagent. Okay, so let's take a look at this problem. First of all, we got lithium metal dissolves in water, and we get lithium hydroxide and hydrogen gas, and then we have to go back and balance the equation. Remember, take that water and break it into HOH, and I think that'll make it relatively easy to balance. And so we're starting out with 5.50 grams of lithium metal. We're going to drop it in 3/4 of a liter of water, and we want to know what the final concentration of the hydroxide ions are. So it sounds a little bit intimidating, but let's just start with the 5.50 grams of lithium. We can convert it into moles, and we can find out how much moles of lithium hydroxide that are produced. Remember, molarity is moles over liters. So I'm going to take that 0.7924 moles of lithium hydroxide over 0.750 liters. Remember, volume's got to be in liters. And it's asking us for the concentration of hydroxide ions. The nice thing about this, it's convenient. It's a 1:1 ratio between OH minus and lithium hydroxide. So if I take 0.7924 divided by 0.750, I end up with a 1.06 molar hydroxide solution, or hydroxide ion solution. So let's take a look at a titration. Titration is used when you have two solutions and you're trying to find the known concentration of one and find the unknown concentration of the other. So the equivalence point is the point at which these two solutions are equal to each other. Usually we use some sort of indicator, or sometimes a pH meter, to tell when we reach that equilibrium point. And so if we do an acid-base titration, typically what we'll do is we'll use phenolphthalein, and we add the base to the acid until the indicator turns a nice light-colored pink. This is a redox reaction used in a breathalyzer test. So when the chromium goes from +6 to +3, what it does is it goes from a orange solution to a clear solution. And what they do is they take a photocell and they measure how much light can be passed through it, and the more light that passes through, the greater the concentration of alcohol on your breath. Okay, so problem number 70 at the end of the chapter says we want to know the volume of HBr. So we're told we're starting out with 125 milliliters of a 0.0100 molar calcium hydroxide solution. So we're going to take M times V of the calcium hydroxide because we're given the molarity and the volume. We're going to convert that 125 milliliters to 0.125 liters. We're going to take the calcium hydroxide and convert it, or moles of calcium hydroxide, and convert it to moles of HBr using molarity. Remember, molarity is moles per liter, so I'm going to put the 0.0105 moles of the HBr solution. And I'm going to end up with 0.238 liters. And if I multiply that by 1,000, I end up with 238 milliliters. So in this case, we're going to titrate some acid rain, and most of the acid or the acidity in that rain comes from sulfuric acid. So here's a balanced equation. We can find the moles of sodium hydroxide by taking the molarity times the volume. Remember, convert that 1.7 milliliters into liters. So it's 0.0017. And I end up with a really small amount of sodium hydroxide, 0.014. We can then convert that to the moles of sulfuric acid. We're then going to divide this by the 20 milliliters, or 0.020 liters. Notice in this one, instead of me just putting the volume underneath, I've turned that into a conversion factor, where we multiply by the inverse, and we end up with 0.035 molar sulfuric acid.